Mm, can the people just check whether it's audible in YouTube?
I don't know. It is showing waiting.
Waiting. Uh,
Mm.
no, no. The link which I sent in Teams. I think the WhatsApp one. I think it is not working.
Ah, okay.
One minute, I'll just check whether it is possible to paste it.
Yeah. Can you speak something?
Is it? Yeah. No.
Yes, yes.
This is fine, right? Yeah. Okay. Shall we start then? I think.
Mhm. Yeah.
Yeah. Okay. I think. So last class we discussed about IKEA. So that is also one of the method for outlier detection. So we went in depth. I think a little bit more of theoretical was remaining. So that will cover later on together along with the Z score. So today we'll go more towards Z score. Okay. So earlier we had discussed about how the data distribution takes place. So generally, when you have a more of normally distributed data, we can use a Z-score method for outlier detection. So when you don't have more of normally distributed data, then we can go for IQR method. So since today it is more of Z-score, so we assume that the data is normally distributed. So what does that mean is basically Z-score is more. It is also called a standard score. It's like once you have normally distributed data, how much by how much standard deviation is the data is getting distributed, more of a scale factor. Okay, so when we come to the formula, it is more of individual data point with respect to the mean divided by standard deviation. So just to go like say a little bit to the background, whenever we get some outlier, the first step what we can do is we can identify the standard deviation, and whatever falls like say apart, I mean within out of the range of that particular standard deviation, we can consider that as outlier. But it purely depends on the problem statement or the domain. Okay, so you can see in my screen, right? So in this example we can see there is some data set. Okay, and for those that particular data, we have 3.4 as a mean value for that. And for this they have identified 1 sigma value, that is 1 sigma standard deviation. And for whatever data falls outside that particular range of 1 standard deviation, we call that as outlier. So this is basic level. Now depending on the problem or the domain, we can say that like say there might be some normally distributed data, and for 1 standard deviation, this is the data, I mean data distribution, and whatever comes outside of that range we might consider that as outlier, and with two standard deviation, this will be the outlier for that. Similarly for 3 standard deviation. So you can see this is more of a scale factor, right? 1 sigma, 2 sigma, 3 sigma. But how do you identify, like do we have any method to like say identify these things in a more standardized way? Okay, so that is when we have something called as Z score. Now if you see, this is like say it is not normalized, right? When we say 1 standard, 2 standard, 3 standard, the values over here, it may be diametrical values or shaft values in case of mechanical examples, but it is not standardized. Even though we identify the standard deviation, in this case say the mean value is 3.4, it is not standardized even though we identify the mean value and then take the standard deviation from that. So that is when Z score concept comes, where we try to where we have a normalized data. Okay, and you have the standard deviation identified with same 1 sigma, 2 sigma, 3 sigma method. But when we try to like say normalize it in terms of making mean value as 0 and then computing the like say standard deviation, that is where Z course comes into picture. It is more of standardized normalized distribution. Okay, so that is what even we see here. So from mean value, when it goes towards positive side, it's more of positive z score value, and when it moves towards negative side, it's more of a negative score value. Okay, but before coming to this, when we go back to, like, say, ground zero, where we identify the data and find the standard deviation here, how do we understand whether the data is normally distributed or not? Because this is applicable only when the data is normally distributed, more like a bell curve. So for that, we have certain tests which can be done statistically. So one point is, where we check the p-value, and then we check whether it's normally distributed or not. Okay, so this is generally a famous test, Shapiro-Wilk test, where we check the p-value and then check the normality of that. So only if it passes this particular test, then we can go ahead with the standard deviation and do z-score test, or z-score value. So this is also, like, KS test is also normally used. Okay, so we calculate again p-value for that, and we check whether it is normally distributed or not. So this will also help in certain advanced concept like hypothesis testing, where even p-value is used to do the hypothesis testing. So these are the general normal test methods. So this will also be discussed in later class. I think we can discuss this method, like Shapiro-Wilk test method as well as KS test method. How can we use those things for hypothesis testing and to test whether the data is normally distributed or not? But this will be a prerequisite to do a z-score test. Okay. So once after that, so what would be the outcome of that? So outcome of z-score would be, one is the outlier detection, and we try to normalize the data. That's what we see here. Okay, we try to normalize it, and other point is comparing the values across different units. Now, since we know that, like, we are trying to normalize the data, what we can do is, suppose if we have two different units of data, maybe something is in kg and something is in, like, say, kilowatt. So we can try to standardize it and then check the distribution and try to compare those two different features. So that is also useful using z-score method. So till now, do you have any doubts? So other point is, it is sensitive to, like, say, the normal distribution. I mean, this is sensitive to mean, because whatever we calculate, it is with respect to the mean here. Okay, so if mean is, like, say, affecting the skewness, or it is forming the few skewness, then even z-score will be affected of that. So it might give vague results for that. So that needs to be taken care. So normality test is must. But we have something called as even modified z-score. What happens is that we can use median for that. So when you use median here instead of mean, then z-score also works very well. So that is more called as modified z-score method. So till now we understood that mean, like, say, controls the z-score value as we see in the formula, and even it helps us to understand the standard deviation in terms of scalability. As we can see, 1 sigma, 2 sigma, 3 sigma, by standardizing it, and then we identify the z-score for that. Okay, so that is again same thing I have explained over here, where z-score works very well, and in terms of skewed data, z-score doesn't work very well. Okay. So, and outcomes are nothing but outlier detection, and even comparing two different features of two different units. So now, if we take, suppose if we take a scenario, okay, other one point what I'd like to highlight is, as I said here, the mean effect. Suppose if we don't want mean to be taken in the z-score, we can use modified z-score. So the modified z-score uses this particular formula, where MAD is nothing but mean absolute deviation. Okay, so we can calculate that, and we can calculate the median based modified z-score. So that is there in this particular yeah, here metric. So if you go here, we have this method here. Okay. So normal z-score would look something like this. So before going for modified z-score, we'll have to calculate mean absolute deviation. This one. Okay. you can identify it. So this is just a absolute method with respect to the observations we have. When we add median for that, that will help. That will form a modified Z score. So I have certain links here. So I'll discuss this. I mean, I think I'll try to share it later because this will give a little bit in-depth insights into that. So this is also one of the blog which I read. Like what exactly does outlier mean, and how can we detect it? What are the different methods actually? So Z score is also one of the methods for under supervised learning. So this we can discuss in later when we start with machine learning series, where what does supervised, unsupervised mean, and semi-supervised mean, and how these outlier detection methods help us. Okay. So even in clustering methods, different patterns of behaviors that can be identified, and how outlier also will be there as a single point in clustering methods. So this is the example which I took and I started explaining. So we have even the codes available there and try to understand whether it's normally distributed and how exactly this particular score method got evolved and why did they use that. So all these things are there here. So next, coming to a scenario, let us take a scenario that you have a measurement. Uh, okay, certain measurements are done in meters and certain measurements are done in inches. Okay, as I said here, we can compare two different features or of two different values. Okay, so where we can use Z score here. Suppose in that example, where we say Z score is positive, meaning positive 1.5, it means that it's 1.5 times the standard sigma value above the mean value, above the mean level. Similarly for negative and zero. So when we say it is zero Z score or nearby to the zero Z score, it means it is the most of the data points are almost near to the average value. That is the mean value of the data set. So that is when I think people who are already experienced with machine learning methods, you might be knowing in sklearn library, we use standard scalar as a method to scale the data or scale the features. So that itself is nothing but this Z score method. That's why it is also called as standard score method, where we standardize the feature between certain range value, like between -1 to 1, and then we fit the value into that, and then we go ahead with the machine learning algorithms. Okay. So just to revise, okay. So what does the Z score equal to zero mean? Okay, this Z score is equal to zero. What does that mean if you distribute the data and calculate the Z score value for a particular data? Suppose we have a shaft diameter of mean is equal to 10 mm. Okay, and your Z score is almost equivalent to zero. What would that mean? Any idea? So that would mean that on an average, the diameters are around 10 mm when Z score is zero. Okay. Suppose for the same data, if the Z score is 2.5, it means that particular set of data is becoming outlier. Similarly, as I keep on increasing the length, you can see here, right? I'm increasing the shaft length. You can see the inferences from that. Suppose if it is 1 sigma, then it means it is above the mean value. That is this particular value. It is above going more than like say 66% of the data or 66% of the shaft manufactured. The deviation is more than that. So Z score helps us to understand in that level, like 1 sigma, 2 sigma, and 3 sigma way. Suppose we have other one case study, okay, where we have a vibration data, and this is the sensor data of the vibration, and we can calculate the Z score for that by normalizing it. So once you identify the Z score for this will be identified as an anomaly for that, and the anomaly will be like easily identified just through statistical methods for us. So it will be either a very high positive or high negative Z score value, which will be above 3. So we'll be able to identify anomaly for that. So it is useful even for time series data, as I said, for sensor or even for some of the strain gauge methods. So we discussed IQR last class, right? So this is also one of the method. I can show the graph here. So using Z score, You can z-score method and IQR method, like how the outliers can be identified here. So in z-score, you can see it is having more bandwidth and it is identifying the outlier only after 7.5 value. Whereas with the use of IQR, which we had identified with the 75 or like say 25% of the data as the like say limit, we identify more outliers here. So this again depends on the domain or application what we use. And other one example is performance of two different engine designs, which may be like say in this one case we try to optimize a design using fuel efficiency and other one using a power output. Yes, Ajay.
Yeah, one doubt. So Z is like it's a deviation which is varying from plus or minus 3, right?
Yes, that is because
And
we are trying
another,
to scale it.
correct,
Yeah,
correct. Yeah, so it's like 3 sigma that way.
yeah, 3
Okay,
sigma.
which
Yeah,
is, yeah, sigma. So where you get it? It's a standard deviation, right?
yeah. That's what initially we discussed here. Now, initially I discussed that we have a data here. Okay, we identify some standard deviation there, and then based on that we find minus one sigma and plus one sigma. Okay, and based on that, as a simple method, we can identify other things as outlier. That's a basic method.
Okay. Mm,
Then same thing, we can say one sigma, two sigma, and three sigma just by increasing kind of a multiplicative factor, right? We'll increase the limit of that.
correct, correct, correct. So it's
But
just
since
it's.
it is a value here, now you are not able to
Mhm,
identify exactly like what is the limit value,
mhm.
because it's a non like say these values can be changing randomly, right?
Exactly, correct. Correct. Yes.
So you try to standardize it. That's when
Mm,
you try to take from this value by using this formula, try to standardize it by subtracting mean value from that and convert that
mm,
into 1 sigma, 2 sigma, 3 sigma.
correct.
Okay, so from
Okay.
that,
Yeah.
yeah, once you standardize it, then we are able to identify the outliers easily.
Mm,
Because when I started the class, I told that this limit can be based on our domain knowledge and the problem,
correct.
2
Correct.
sigma, 3
So
sigma,
it can
something like that.
shift. Yeah, it can
But we
shift
can't
to whatever.
standardize it here
Right. Right. We
because
can
the
shift that value. I
these
mean,
values
yeah.
might keep on changing. But
Mm,
to like say I want to compare one feature with other feature,
mm.
then we need to have some common unit.
Excess.
So
Right.
that
Right.
neutral unit is nothing but z score.
Mm,
As I said in this particular example, we might be having a scenario where you have a like say fuel efficiency and horsepower.
mm, mm.
Both are of two
Right.
different units, so you can't compare it. But if you convert both into z scores,
Mm,
now you know with the relative distribution of the data and with respect to standard deviation how the two different features are behaving with respect to each other.
right. Right.
What is the
But
average
in
value
in a,
among that?
for example, okay. For example, if I take the fuel efficiency of, is it like different vehicles or like is it
It can be for different vehicles also. That can also be
so?
compared.
Okay. So yeah, so we can take it as a mean of somewhere in,
Yeah,
if it's 18 or 20, and then we
like
can
one
whatever
particular
comes.
car
Yeah.
might be giving a certain fuel efficiency, and other car might be giving some other fuel efficiency, right?
Mm, mm,
So you can put Z score for one car and another Z score for value for other car,
correct. Correct. Yeah.
and then it
But
means yeah,
we need to have data sets for all the
yeah, yeah.
cars,
We
right?
need to have data sets for that.
Mm,
So other one is also like how can that be used for machine learning? So data normalization, as I said, right?
mm, mm,
You can normalize the data. So in standard scalar, what we use, this is one of the general library what we use in sklearn when we do machine learning. So that's also the same formula as Z score. That itself is Z score actually, where you standardize the data between 0 to 1 in this case. Okay.
mm.
Or we can use something called as min max scalar, where you can even change the domain, like from -3 to 3 or -1 to 1. You can set it there.
Mm-hmm.
So we can use that method, and I didn't use the different features, and because it is more useful. Because like say this is in degree Celsius and this is in RPM. Both are two different units. And in machine learning, when you have two different units, sometimes the learning process it will not capture those features properly for prediction.
Mm,
So that's when we need to scale, standardize, or scale the data in a particular domain value that is from 0 to 1.
correct.
So it will be like say in this case, if I say 0 to 1, it might be possible that if 50 will be 0 and 200 will be 1. So temperature will vary between that. And in this case, the 500 will be 0 and 5000 will be 1.
Right.
So that scaling will be in the common neutral format.
Mm-hmm.
So that will be useful for the machine learning algorithm mathematically to like say bring the pattern.
Mm-hmm.
Okay. So any questions till now? Because after this I have one simple exercise, and I think after that we can wind up this session. So this is just a simple concept. Let's score.
Mm-hmm.
So any questions till now? Because this is more useful. This is like recently I had worked on one particular data where I had a time series data. Okay, I just simply use its score to identify the anomaly. It works very well.
Mm-hmm.
I'll try to find some Kaggle dataset where we can identify time series and identify the anomaly in future class. Maybe in next class I'll try to identify any problem for that, and we can have that live session.
Can we get some papers? Okay, maybe in the internet.
Papers, I'll have to check
Can
for
and
that.
then
That's what I'm
yeah,
just checking for dataset which is available in
correct, correct,
open source.
right. So in the paper also it might be there, right? Data
No, it
sets.
might be there. I
Yeah.
think you can, even if you go and check anomaly detection, yeah, I think you can see here, right? So continuous sensor data. I think you can just sign in and check the data sets. You'll be having that.
Mm-hmm.
So okay, yeah. Yeah, you can see it here also.
Building out some of these anomaly detectors.
You can see it here, right? See, this is one of the anomaly. So Z score will be predicting this very much easily because you have the mean value in that, right? X minus mu.
Mm-hmm.
So mean value for a particular, so we have some terms in time series, what we call as seasonality and all those terms. Okay. So that will be discussed when we discuss time series methods. But when you see here, it has some pattern in that. When some point comes away from the pattern, it is able to predict that using Z score because we have some mean values detected for this when we calculate it.
So we're
Yeah,
operating.
I think, yeah, even here it is able to identify that. So as you can see here, they have said outlier detection methods. So you can see here, right? So this is not normally distributed, kind of normally distributed, but not. It has some skewness in this. So there will be certain techniques where you can remove the skewness and identify that. So even here you can see mean value will be somewhere here, right? So it is identifying some outliers here.
Mm-hmm.
So you can see servo motor current data. So they have the data for that. So even for vibrations, we are able to identify in a similar manner. Think even here, yeah. So you can see this certain vibration patterns, or in this case, it is a current data, and they are able to identify certain patterns there. So you see, even this is also machine learning only. What they see here, this we had discussed in initial classes, right, regarding the bar chart and all the stuff statistically.
Mm-hmm.
So these parts, feature sorting, we'll discuss once we start machine learning. So yeah, any other doubts? If not, see, I have a data set here. Okay, so this is these are we have a scenario where we have a bearing life being measured. Okay, so there are around 10 bearings, 10 different bearings. We have a lifetime data for that. Okay, so now we need to identify Z score and give some inference for that. So first step, what we need to do, like we discussed, right? uh, Z score formula, it's an individual
Yeah.
data point
That's
with respect to the mean value with respect to the divided
yeah.
by standard deviation. So when I have a data here, we have a lifetime data here. So what would be the first step we need to do here?
Mean we have to calculate.
Yeah, mean we need to calculate, right? So we have 10 different observations here.
It has
Yeah,
add up and divide.
you need to add up all these values here. Okay, some this value x values, that's individual data point, and identify the mean value for that. So the unit is in hours. Okay, then we need to calculate the standard deviation. So we know the standard variance formula, right? I think somewhere, yeah,
Mm.
here I have written that xi minus mu, that is again individual data point with respect to the mean value whole square divided by the observations. So again I have calculated that over here. Okay, so that is what they have run. And then so individual data point, that's 1200 minus mu, that is the 1243. So you got minus 43 as the value, x minus mu, then the whole square of that. So when you calculate for each and individual value, then identify the, sorry, calculate the total value for that. Okay, then use this formula to calculate the standard deviation. So once you identify the standard deviation, then you use this particular formula, right?
Mm.
So x minus mu is done. Okay, now you know calculate z score. That's x minus mu divided by sigma.
Mm.
So sigma we calculated standard deviation. Okay, so it gives point minus 0.72. So now you
Mm.
know the z score is negative. It
Correct.
means it is below the mean value, right? It means in this case it's the average lifetime. This represents the lifetime. Mean represents the average lifetime. So here we can say it is slightly below the average lifetime. That is what it is giving the inference from z score. Similarly, 0.12 means it is above average lifetime. So little bit above the average lifetime. Maybe like some shaft, or sorry, in this case the bearing is operating. We are having some average lifetime for all the bearings, 10 bearings. So we can say the bearing 2 is performing little bit above the, it might come, the life might be little bit more than the normal operating average life. In this case, it is coming minus 1.06. It means there is a possibility of failure, right? So it may be a concern when it's minus 1.06, when the z score values of that value. Similarly, okay, now you know, like you can see what are the inferences from different z score values, right? Now let us say I am changing one particular bearing number ID 7. I am changing the. It is like say the sensor is not. I mean, it has not captured the life cycle properly, or the data is not proper. We are trying to recalibrate the sensor, and we are calculating the life cycle again. And we have again recalculated, and now it is coming as 1000 instead of 1001 Okay. So what does that mean? Again, your values will change, right? Mean value
Mm.
will change, because you are recalculating that, and again your standard deviations will change, right? So since standard deviation and mean values changed, even z score will change, right? So overall again it gets impacted. So now if you compare minus 0.72 to minus 0.3, it has changed the value, even though this lifetime is same. So you can see how the values are getting affected in a particular data set if it is not, if the data is improper. So now, since 1000 has changed, now you can see it is significantly like negative. Earlier it was around roughly minus 1.56, right? It was almost like minus 1.5 sigma. Now it is almost 2 point, like 2.5 sigma, something like that, right? It's a strong outlier now. Earlier it was more like just a concern. Now it is purely outlier, and you can directly identify that the operation. So when you calculate all these z score values, we have something called a z score table. Okay, this is like theoretical method.
Can you put that YouTube video up in the chat?
Yeah, yeah. This one, anomaly detection.
Ah, correct.
So generally they do it theoretically. Now here in this case we have programming libraries. That's why we are able to do. But in theoretical method, they calculate as I've shown in this current example. They calculate the z-score value, and then they go to the table and they identify that. Okay, so they check it here. They go to this table here. What's the z-score
Mhm.
value? And for that value, then they identify the normal distribution probability of that. Okay, yeah, here it is there. And from this they are able to identify the probability of the, like in this case maybe failure or something like that. So this is very much useful in case of your hypothesis testing, or even in terms of probability, that what is the probability of failure.
So what is that table telling? Can
This
you?
is the z-score value table. Now we identify the
So
values, right? Yeah, from that value, now
mhm.
you can say what is the probability that it might, like say, fail or not. In this
What is
case,
there in the horizontal and vertical
this
axis
is
in the?
the like Z value, Z score value here. This is the probability.
Okay. Okay. Okay.
Like probability of failures we can identify.
Mm.
So this I'll try if I get some problem where we can try to
Mhm.
like do it manually. Go to the table and then identify the probability of failure. Maybe next class I'll try to do that. We will try to do this thing theoretically and even programmatically. Like some Python code, I'll try to get it. Maybe for same bearing failure, we can identify how much life is left for that bearing to fail based on the outlier.
Mhm.
Okay. But this is more of theory. Just wanted to explain
Mm.
for Z score. So any doubts? So if no doubts, I think we can close the session. Or if any improvements needs to be done, any more data needs to be added. So this Z score method, in terms of FE also we can use it. Suppose
Mm.
if you're having failure data, so we can try to put the Z score. Like say if you have two different data, strange case data or even stress failures data, so you can try to put it normally and then identify the Z scores and do it. But I don't see much of a like say usefulness. But in terms of realistic data, test data, if you have, it is very much useful in comparing two different designs or something like that, or even taking some decisions. But this is what is the background. Like you can go with like initially standard deviation was calculated, and then to bring all the different features into normalized or say neutral format, they started introducing Z score so that that can be put into like 1 sigma 2 sigma method by neutralizing it so that multiple features can be combined. And then some drawbacks related to mean effect were modified using modified Z score method by using median instead of mean value here. But again, it purely depends on application. So most of the times mean will work very well, but if mean doesn't work very well, then we can go with modified Z score. So in programming wise, I think it is better to use both options and check which is giving better result. Yeah, so if no questions, I think I can close the session. Okay, let's close it.